Go to eat lunch.
Go to eat lunch. Oh, because what? Yeah, cannot wait for that. Okay, your group is group 1. Semester, sorry. Sem 1, group 1, right?
Sem 1 group.
All of you. None from other group. Anyone here repeat? No. Okay, I sent the slide here. Yeah, sure.
自己写还
Class replacement for Thursday.
自己公司还那个上
First is on 28 March.
不是吗？
The other one is 11
我让他自己写。
April. This is the one that I
哇，这样不
My proposal is on Monday, 1st April and 8th April. I think it's alright, right? The timetable I already checked. The slot is, oh sorry, I did not put the time. Time is, I think 2 to 4. And then you have a class after that. 4 year class, right? On Monday. Practical class. Replacement also. Is that right? Monday. Two, three,
皮肤线我是长什么？
You have class replacements from 4 to 6, is it? On the 1st April, is that right?
1st April.
I don't know. There's one. I saw that there's a class replacement as well. But I put it as 2 to 4. Is that right? I mean, after this, you have a replacement. Somebody already checked.
Something 2 1st and
What was it? Also the same, because it's on Thursday as well. Sorry. It falls on Thursday. And I changed Monday, 1st April, Monday, 8th April. There are 2 days there. Okay? 2 days holidays. 4 on Thursday. That means today's class. Not today's class, I mean it's already Thursday class. So I moved to Monday, 1st April, Monday, 8th April. Okay. Okay, lecture, I have no choice. I have to do it late in the evening, too late. This is after 6, because there's one class, they finish also at 6 on Friday. Other days, I think all of you are packed as well. So you have to be done on 6 to 8. Okay? And I choose Friday because Friday is the only day that only one class has 6 to 8. The rest of the days, a lot of you has until 6 o'clock. Okay, also I'm free here on Friday because other days I'm quite busy as well. Okay, so that is the lecture. This one is for your group practical class. Okay, Thursday and both Thursday, 28 March and 11 April. Okay, let me know if there's any issue. The venue will be here. Practical class is always here. Okay, let's go to this practical 4. Okay, practical 4, we are going to look into critical region and how to use what we have learned last week. In fact, later on also, I'm going to continue on this critical region, how to solve it. Here we try to do it on our own. We don't want to use fault reduction. Fault reduction actually handle the critical region for us. But here we want to learn how actually critical region is handled. Okay. Now, why do you need why there is a critical region? Okay, if we have any shared data, okay, where you do read modify write. Read modify write. That means shared and also read modify write. Okay, and things are executed concurrently. This one needs to be protected. Okay. And whatever that is done here, we call critical region. Right? Okay, code involving this shared data with read modify write. Okay, this code here is called critical region. Okay. Code that is involving shared data and we do read modify write by multiple threads, not a single thread. Single thread, no problem. But multiple threads, shared data and read modify write. The code that is handling this is a critical region, right? So how do we solve it? We solve two ways. The first way is to use partial sum. Okay, partial sum actually avoid the shared data. Because partial sum, each thread has its own partial sum instance, right? Even though the array is shared. Okay, so what I mean is this. So you got a partial sum, and okay, depending on how many threads that we have. So T0, T1, T2, T3, and then Tn. Okay. So all of these threads here has its own instance. So whenever they sum their partial sum, they are only read, modify, write their own instance. Okay, they do not touch any others. So in this case here, this partial sum, even though it's shared, okay, even though it's shared, but it does not have this read, modify, write happening on other instances handled by other threads. It's only read, modify, write on its own instance. Okay, so these are not considered a problem because it will not cause any race condition. Okay, but this one, yes, this sum is a shared data. If everybody is trying to write into it and they are doing read, modify, write, okay, the code that is handling this is called critical region. Okay, so what we have done last time, we avoid this by doing this. Okay, but then we still have a problem. Because why? Because in the last part, all of this need to be summed into this shared data, which is called sum, the same as this. Okay, so somehow we try to avoid it, but we cannot avoid it completely as well, right? We can actually, how to say, we can mitigate the problem by doing a partial sum, which solves that problem. But in the end, these are partial sums. They are not the complete sum, right? So you have to sum them up together. And you still have this problem, the same problem at the end there. But it is also mitigated. Why? Because here is done by, this one is done by multiple threads, but the last one is done by single threads. Okay, done by multiple threads. But this part here is this part here is only done by single thread. Right? If you look at the code, this the sum, that sum, all this up, the for loop that sum all this up is actually outside the pragma OMP parallel. Right? So this one is inside the OMP parallel, but this one is done outside the OMP parallel. Okay? I will put my code here. This is a code. Alright. Okay, so you can see here, it is done inside the OMP parallel, which is the partial sum. Okay. And because it's done by multiple threads, right? Okay. And each individual theory modified, right? But they are not overriding one another, even though this partial sum is shared. Okay, it's partial sum. It's only shared, it's outside. Okay, it's declared outside. Okay, so this one is done by multiple threads. But look at this one. The last one. The last one is actually to sum all of them up together. So you use for loop to add them up together and put value inside. But here, it's outside. It's outside this pragma OMP parallel. So there will be no race condition, right? Because it's done only one thread. Right? And also, the thread that is doing this will wait until all of this is done. Okay? So what happened is from top down up to here is done by one thread. Inside here is done by multiple threads, and you wait until all the threads finishes before the one thread is going to execute this. So this is also done by one thread, but it's going to wait until all of them finish first. Then we execute it. That means here, because if everybody has finishes, that means everybody must have their whole complete partial sum, right? So when you get out to here, the single thread that is going to execute it will be able to sum them up correctly, because once you reach here, all this partial sum has been completed correctly already. So it's going to sum them up. So you can see that this one is problematic because it got race condition. But we mitigate it by doing this. Okay? So this one no race condition. This one also no race condition. So we solve this without using mutex or binary sum of 4 to solve this problem. Okay? But of course this one has problem. We have a fault sharing, and then we deal with the fault sharing by spacing it out, right? See this, we do padding there by 64 byte. So that solved the problem partially, but then the performance was not so great. Okay, we look at the performance. Here is the performance. The first one is single thread. The second one is fault sharing, even worse than a single thread. So we solve by doing padding. We get some improvement here. But the improvement here is only 3 times faster. Okay, without padding, that means fault sharing is worse than single thread. With the padding, okay, fault sharing, we eliminate the fault sharing is 3 times faster. But if we use fault reduction, this is fault reduction result, it's about 6.5 times faster, or about 7 times. Okay. Okay, so let's get back here. Okay, so we're able to solve, but then it's only 3 times faster. Okay, so we want to find out if we can improve this. Okay, so we try to also solve this by using mutex. Okay, we don't want to go around it and then solve it this way. We want to use mutex to solve it. Okay, there are 2 ways to solve this kind of problem. Let's have a look. Okay, we're going to use lock. We're going to use this lock here. Okay. Now, I mentioned to you last week the lock that we have. Has block is a technique. Sorry, it is a group, a set of techniques to avoid race condition. And we have multiple solutions. One is spin lock. The other one that we learned is binary semaphore. Okay. And the last one is mutex. Actually, there are a few more. Another one which I will cover in chapter 5 is monitor. Okay. Now all of them are locked. Okay. Now spin lock, binary semaphore, and mutex. It is especially this binary semaphore mutex. I'll show you later in the lecture. You can make mistake. Okay? If you are not careful, you can make mistake. So they know that a lot of programmers, especially beginners, they make a lot of mistake, and that mistake can cause deadlock. Deadlock means the program will not progress. No program will progress. In order to recover, you have to reset the whole computer or shut down the computer, shut down the program, and then restart the program again. And that can be a problem, right? So if you make mistake, you get into deadlock, and deadlock is actually an unfavorable situation. So in order to prevent that, they introduce new type of lock. It's called monitor. And this monitor is very hard for you to make mistake. Okay? And what we're going to see here is monitor. We're going to learn binary semaphore on the text later. I'll show it to you. Okay, binary semaphore and mutex, I think we'll cover in practical 6. Practical 6 we're going to use this. Okay? But for now, because we want easy, we use monitor. Okay? Now how does the monitor look like? Monitor looks like this. For example, you can look at your it looks like this. Now OMP critical, and then you specify what are the shared variable that you want to protect. Okay? So this is a monitor. And it's very simple. It doesn't have up, down, or wait or signal. You don't have all this kind of thing. Okay? You just monitor OMP critical, and then you enclose the critical region inside that. That's all. Okay? And you will not make mistake. I'll show to you that these two how you make mistake, and this mistake can be very severe. Okay? If you are not careful. So this one you will not make any mistake. Later on when you learn this, you have to be careful. Which is the practical 5 or 6, I can't remember. Okay, another keyword that probably we have learned before is this shared variable, right? So you see, firstly when you go to the parallel section, which is specified by OMP parallel, we need to specify which one is shared. Okay? And then inside this region here, you need to protect, because this region is going to run parallel threads, right? That means every thread is going to run concurrently or in parallel. And therefore you can face race condition if, let's say, the shared data is read, modify, write. Okay? Now in that region, there's certain region that when you do read, modify, write, especially the shared data, then you have to enclose it within this config record, which is the monitor. Okay? It's not this monitor. You call your screen monitor, but this monitor is the monitor that I was talking about, which is a lock. Okay, it's just a name. Okay, now I'd like you to try this. This program has been done by you, right? Yes. This is a fine pi here, and the solution is given there. And this is solving the problem without eliminating the fault sharing. There will be fault sharing inside it. But this is a solution. The solution for the previous practical exercise, but not the solving the fault sharing. Okay? But it solved using this type. Okay? Now, we want to modify this code to use monitor. Okay? To help us solve this problem. There are two ways. The simpler way is to use sum to protect this. Okay, you protect it. I draw a box, that means this one is protected. Okay? Okay, so that's the first way. Now the second way is to split them again to this partial sum. Okay, why do you want to split? Okay, let's have a look at this problem first. Now, when you do OMP critical, even though you don't do binary mutex, binary semaphore mutex here, but this monitor actually implement this binary semaphore, and either one, I do not know which one. And we use monitor because it's simple and it's very hard to make mistake. But the implementation, if you look at the implementation, if you have the source code, when you look inside that, actually it uses binary semaphore, either binary semaphore or mutex. Okay? Or maybe spin lock. Okay? So it means that if threads comes inside here and then perform this critical section or critical region multiple times, it means you have to acquire or perform a down, and when it finishes, it perform a up. That means it releases. Okay, acquire, release, acquire, release. But we have how many here? How many times that we need to do? Here is about 1,000, so 100,000 times. But I suggested you change it to 1 million. That means you have to do this 1 million times. Not so good, right? Because this will be taking a lot of time. You can check the performance. Okay? Later on you check. First method and the second method. If you acquire and then you release, acquire and release, and you have to do that 1 million times. Okay? So acquisition and releasing actually takes a lot of time, and we do not want that. Now, how do we overcome this? We come back to this partial sum again. So in the second method, what we do is we have partial sum, but this partial sum is not shared. This partial sum is local. That means it's private. Okay, it's unlike here. This one is shared. This one is local. Okay, so that's the first idea. The second idea is when we do the sum for each thread, because it's local, it will not be having any race condition, right? Because local and private will never have race condition, isn't it? Cannot? Sorry, I made a mistake. I shouldn't draw partial sum like that. I should draw only one. Okay? This one is different. This partial sum, because it's an array of partial sum, okay, and it's shared. This one, partial sum as well, but it's local, and it's only one. Because each thread has its own one. Okay? So when you sum it in here. Do you need to protect with the critical region? Do you need a critical region to protect this? You don't, right? Because it's private. Remember I mentioned to you, critical region code, the code that involves sharing data with read, modify, write, and run by multiple threads, this needs to be protected. And that protected region is called critical region. Okay? Because you want to avoid race condition. Now, if it does not satisfy any of these conditions, that means you will never get into race condition and you do need critical region to protect it. Okay? Okay, how do I know? If read, modify, write, run by a single thread, do you need to protect it? No need. Multiple threads, read, modify, write, do you need to protect it? Yes, because you would have race condition. Now, how about multiple threads? Read only, no write. You read only, but you don't write. Do you need to protect it with critical region? Huh? No need. No need. Why? Because there's can never happen race condition, alright? Race condition happens is only when you read, you modify, and then you write it. Okay? But you're reading only, you're not modifying. So the data will never get changed. And therefore, it will never get into undeterministic result. Meaning that you don't need critical region to protect it as well. Okay, so you must understand why do you need this critical region. I mean, no, you don't need this critical region. You have to identify which one is critical region. That means that code is not critical. Okay, it's not a critical code. You don't have to protect it with any of this. Because it's just reading, even though with multiple threads. Because it will never have race condition. Okay? Okay, so this partial sum is private. It will never have any race condition in there. And therefore, it is the code that's handling this is not considered as critical region. And you don't have to protect it with any one of this. Okay? So this partial sum is just like this, but every individual thread is going to calculate its own partial sum. And you don't protect it, and then therefore you don't spend the time acquiring and releasing it, so it's faster. Okay? Next, what you do is you add the partial sum. So this is the first step. The second step is add the partial sum to the shared sum. Okay? So your partial sum, which is this one, which is private, but you add it into the sum, which is shared. Now, the code that's handling this, do we need to protect it? Do we need to protect this code here? The partial sum, which is local, which is private, you already calculated. Once you have it, you have to sum it up into this shared sum. So that means you're writing into this sum. Now this code here, that's executing this part here. Do you need to protect it? Yes, you need to protect it. Why? Because all the threads will take its own partial sum and add it into the shared sum. And they are competing with one another when they are writing into the shared sum, right? So you have to protect this code here. And that code is a critical region, which you have to protect with one of this. We're going to use this monitor, which is OFP critical, right? So only this one that we need to protect. But how many times that you need to do this? For each thread, how many times? One time only, right? So each thread only one time, and if you have 16 threads, in total here, 16 times only execute this. This will be faster than this. Because this one have to do 1 million times. This one you have to do 16 times. Is it correct? Because each thread is going to do this only one time. And you got 16 threads only. This will be faster, right? So you have two ways. This is the easy way. This is a more difficult way because you have to involve partial sum. But although it looks difficult, but actually it's simple. I want you to try this and this, right? So here, because it's protected, so you have to do gamma. Here you don't have to, because here is local. There's no race condition. So here, pragma, OFP, critical, and you have to specify what are you protecting. It's the sum that you protect, not the partial sum. The partial sum is private, so you don't have to protect it. Only the sum which is shared, and it has a, you have to do read, modify, write, so you have to protect it with this critical region, right? Now, if let's say you have many variables, shared variables that you have to do read, modify, write, and you have to protect it, you have to add it here. So sum, comma, followed by whatever variable that you want to add in here, right? Now I'm going to show you my code first, so that you can refer to it and use it as a reference. Don't copy it, because I see the other group, they copy and then change it. They change it exactly like my original copy, and it doesn't work. Because the one that I'm going to show to you is a different problem. I just want you to refer to it. Don't copy it and then, copy the code into here. Because if you copy the code into here, you won't get the result. Okay? The result is, the program is different. You just look at my how I solve it, use it as a reference. Okay? Because I'm lazy to go and do it right at the beginning and again. Actually, I already done it. But I'll show you the code. Okay, while waiting for that, let's just create a project. Same project I what we have done on SO app and through C++. SO app here. C++, next. Give it a name. I'm not going to use this, I'm going to use mine. Maybe I should use just give a button.
console app.
Okay. Okay, first thing is include the arrow string already there, and then include idle money because I want to change the number of decimal points when you print out the floating point. Then I include OMP when you create the project because you need the OMP. Please go to here, right click, go to properties, go to C++, go to language, go to here. And click on yes. You don't do that, then you'll be running on a single thread and you're not going to run on multiple threads. And your result will be wrong and you will not do any good. Okay, click OK. Okay, I'm going to call max size rather than max. You uses max there. I'll change the name to max size. And I don't use define here because I'm using C++. C++ prefer not to use define. C++ always prefer to use a normal variable and then you put constant keyword or modifier in front of this integer. Okay? This is actually a constant just like define. Okay? In C don't have this keyword of the modifier called constant. Now in C++, we do have it. Okay, so in C++, we prefer to use this rather than define. Okay, use this. And then I add in using namespace std because I'm lazy to std always. Okay, this is the original program. In the sum. Yeah. Oh, sorry. Before this, let me show you my code first. Okay, this is the original code. If you don't have it, refer to this. If you mistake, it is all here. You go to here, you will see I posted for you already. Right? I posted for you here. That's the sum. That's mark E. This one is without fault sharing elimination. Yeah. The version 2, I eliminate the fault sharing using the padding family. Okay, and then this is fault reduction. Okay, and the result is shown here. This fault function and the result. Alright. So refer to this for the previous example that I showed you. Actually, I also have to put it here. It's exactly the same. Okay, and then what is it? Oops. Okay, I did not have that. I only have the original one. And then this is the code where I use the OMP critical and the shed keyword. Okay? So the previous program that I showed you in the email is solved using partial sum without the fault sharing elimination and also with fault sharing elimination. And I also give you the solution for fault reduction. Now, for P4, I modify that code to use OMP critical, so I should do that. Okay? So how do I do it? I put everything inside the OMP parallel, including the one that sum is. Okay? And take note, because I sum it inside the OMP parallel. And this sum is read, modify, write. It's done by multiple thread. So I have to protect it with critical region. It's a critical region, I have to protect it with OMP critical. And I also specify which shared data that I need to protect, which is the sum, not the partial sum. Partial sum is local, it's private, you don't have to protect it. You only protect the sum. Okay? And this technique here is the second technique. I don't show the first one, you're going to figure out actually it's very simple. You know. This one is maybe a little bit more challenging, but it's a simple. I showed you this, I did not show that. Right? So I use partial sum, and that partial sum is local. It's private. There's only one. It's not a array, but it's a scalar. Okay? It's only one. Scalar means one. Array means multiple instant inside. Okay, and when I do the partial sum, you see it's outside this critical region. Why? This partial sum is private, so it will never have race condition, and it will be faster as well. So I put it outside. Okay, and I sum them up together from I equals to ID, and then when I increment the I increment accordingly. I need to increment by the number of tracks. Okay, so that we control the tracks. And there is some differences between the old code and the now is that I specify explicitly how many threads that I want. I put another thread, I force it to 16. Okay? Because on your machine it might be 8 by default. I do not know. So if you do this way, then you'll be correct. So if let's say you do it at home, you find out it doesn't work, change it to this for the old code as well. Because this old code is a hard code. You see this 16 there? I make assumption that the number of threads by default is 16. Now your machine can be 8, can be 4. Okay? So if it is 8 and 4, you have to change this accordingly. Now, if you want to force it, you do it this way. You do it this way. You create a constant integer total threads. You specify how many you like. Here I put 16. You can put 32 if you want to, or you can put 4 if you want to. And then in the pragma, I say OMP parallel. I want to instantiate only the number of threads. So I put num threads, total threads, which is 16. I force it. Okay? And here also, because I force it to 16, I know that it's 16. Then here must be 16. Yes, sir? Okay? So I don't make assumption in this case. Okay, my old code will work on this machine, but will not work at home. If you go back home, it will not work. It might not work. It will not work. It might not work because it depends on the default number of threads on your machine. On different machine, the number of threads will be different. Okay, so in my old code, I make assumption that it's 16. If it does not work at home, then you change it to like this. Instead of forcing it to a value 16, you click constant integer, total thread 16, non-threads, total threads, and then here you put total threads. Okay, what I mean is this. This is the code I gave to you, right? It might not work at home. So you have to change this to non-threads. Sorry, total threads, total threads, total threads. And here non-thread, total threads. Okay, if you do that, then it will work at home as well. Okay? Otherwise, it might not work because it depends on here, my code here. I assume that the default number of threads on the screen is 16, which might not be true. And here also the same thing. Here should be total thread as well. It's not total threads. Okay? Change that. Okay. Coming back to here. So you can see when I do the partial sum, right? I don't put it inside the OMP operator because I don't need to. And if I put it inside, it will be slow. So I put it outside. Right? And this OMP operator, there's only one. There's no for loop there. Here, there's a for loop, right? Why? Because it's done by one thread, a single thread. That single thread is going to add one by one. So you have to go into for loop and add one by one. But in this code here, no. Why? Because it's done by the individual thread itself. So all the threads is going to execute this code here. So you don't need any for loop. Okay? So remember that this piece of code here is inside the OMP parallel, right? So all the thread is going to do it. If you look at the original code, okay, the OMP parallel is here. And this code, which is going to be executed by one thread, is outside. It's outside this OMP parallel. That means this single thread you have to add one by one. Okay, there's a difference there, right? So this is the version 2, which eliminate the fault sharing and it solved that. It solved this critical region without using monitor. Okay, using this technique without using the monitor. Okay, this code here is using the monitor, that means using one of this log, which is the monitor, and it happens here. Okay, and this code is inside the OMP parallel and is only done once. Okay, and because each thread is actually doing its own job. It takes its own partial sum and sum it out. Okay, now you're going to refer to this code here. You can take a snap photo if you want to. And done. Okay, refer to this, not copy, refer to it. And get back to here. Go to this code, download it. Already have it, it's here. Okay, copy this, copy all this, and then paste it inside the project. Basically, I already pasted mine. Yeah, I pasted it here. Okay, I paste it, and I call it average of some symbol. Oh, sorry. This is not the code, I'm sorry. Maybe I have to do it. Let's copy this. That's not the code. Yeah, paste it here. And I change this to double because I want to return the time. And let's call it find pi. Find pi. Multi with 20 return. Okay, we're going to improve this code using my picture. Alright? Okay, there are some changes that I want to make here because I don't want to repeat many times. Okay, first thing is the num threads. Num threads. Maybe I can put num threads. So I don't want to use define. I want to use this constant because this is the recommended one in C++. We don't use define. We use num threads. Sorry, we use constant integer and assign instead of 4 it was 16. Okay? So that's the first thing. And then this num steps is actually max size. Because I already have max size in my code here, I'm not going to use this. So I'm going to use my max size instead of num step. So num step, I'm going to change here. What else? Is there any other num step? Yeah, this one. Good. Num step. Come on. Okay, so I change that. And I remove this. Okay? And this step here, I don't put it outside. I have to put it inside. Let's put it here. Okay, put that. Remove it. Okay, these two, I already have it at the top there. So I remove this as well. Okay, this one I already have it. So, okay, so basically it's just this. Okay, there's one more change that I want to make. This one is
ทำไม
extreme
ใครเลยนะที่สิ
because I think it's kind of silly also. Because I force it to 16, right? But this code here is actually getting the first thread 0, to go and find out what is the total thread and then put it inside this thread. So that it can be used down below. But I found out this one is kind of silly because I already forced it to 16, right? So I know that it's going to be 16. Because I know that it's 16, I don't need these steps here. Okay? I don't need this. Because I know that I want 16 here. Okay? I set the one big number of threads and set the 16. Okay, but because I do that, now I have to change my code slightly. Here will be this. Okay, you want to write that, you need to change it to this. So here is the num threads. The same thing for this. This will be num threads. Any more? No more. Okay, that's all. Now, do I need this? I don't need it as well, so I will. There's no need for it. Okay? Okay, another one, because I changed the double here, I need to return this. Okay, so I return the end time minus the start time, which is the duration of the what. Okay, so I have C out there, C out the problem. I'm not sure it's already there on the screen. STD, that's correct. I'm not sure why the C out is there. Maybe we can run it. Let's find I. This is the original code. The original code, let's see whether it works.
step พ่อของซื้อนี่แหละ step มันจะเป็นตู้ห้อง step
from. Put that column and see what's wrong. Oh, sorry. Okay, so let's try again. Oh, sorry. Yes, I have this. Let's remove this. Run this. Okay, it works. Yeah. So the value is correct. 14159. Okay, there's one more thing that I want to change there. Instead of doing that, okay, I can remove this. I can remove this, but I have to remove this semicolon at the back. Okay, and then also I want to change the position. So I set position 7 to 12. This does not print anything, just like this double print for double and put to 12 decimal points. Sorry, 12 decimal points, 12 decimal. On it, and you see longer. Here's a longer because I set the position. Okay, and look at the amount of time taken is this much. All right, and I can compute it. Just look at that. So this one works. Now I want to copy this. So this one is withdrawn. Okay, this is 5 with WebP. Sorry, this one is without WebP. This is original one. That's what I mean. Okay? This is the one that we need to modify. So this is the original, and that is the modified one, right? So the original is going to be here. Modified one. And then I'm going to take this and print out the performance gain. Yeah.
Later, copy the code into the ParallelComputing tab. You cannot keep up with the speed.
What?
Later, can you copy the code into the chat or you cannot keep up?
Yeah. Okay. So that's what I did just now.
这个快拍了，
这里 copy 原本那个，然后你原本的改成这个名字，然后现在这个是 modify。
But this is the original code. I just changed the num-thread size around to make it okay. And then write your own code. Refer to this. Refer to the original code. And call it find pi multi equal to 3. Right? So your job is to refer to my original code and then modify it. Don't copy my code. My code is just showing to you how to do it for my previous problem. So use that same idea here. Okay? So you're not going to have an array of partial sum. You're going to have local private partial sum, which is scalar. This one is array, this one is scalar. Scalar means only one. So here is array, right? You have to make it scalar. And here is also shared. You have to make it private. Okay, that's the first thing. And there's no for loop here because it's not going to be done by one thread. Okay? It's going to be done by individual thread itself inside the OMP parallel. So you have to move that in. Okay, and then identify which variable that is shared and re-modify right. And protect it with OMP variable. Okay? So refer to my old code and then do the change and then compare the result. Okay, so you are doing this. This is the one that the exercise asks you to do, but you can try this. Okay, doing this is simpler than this. You do not need partial sum there. You just use the shared sum. Okay, this is going to be slow. This by right should be faster. Okay?
有 error， 你要
Okay, let's call this version 2. And you have version 1 as well. But this version 2 is version 1. You can try version 1. I show to you maybe how I do it for version 2 and version 1. This one is version 2, which is the bottom one. Okay, I'm going to show you how I do this. Solve this is using version 1. Okay, now this is my problem. This one, sorry. This one. Okay. So this one is my own program. This version 2. I'm going to solve this using version 1. Okay. So version 1, I do not need partial sum. Okay. And when I sum it, I sum it here. And because I summed it, I need to protect the comma. Like this. Here is a bad idea. Here you can see that it's shorter because I do not need partial sum. In this case, I do not need partial sum. This one I need partial sum. And you see this folder there? This folder is going to be 1 million times. Because I got all 16 threads shared among all of them. But it's going to run this again and again. Go in the critical region, come out from the critical region, enter the critical region 1 million times. So it's not as good as this. Okay, you do all the how outside, and then you enter into the critical region 16 times only. Each one thread, one time. So you got 16 threads, so 16 times. Here, this follow is going to be executed by all the threads, and each one of them have to do it, right? And it's going to be 1 million times, and this is going to be slow. Okay, so this will solve the problem, but it will not give you much better results. So let's put this as version 1. And I have another one, version 2. Okay? Okay. Let's see.
이거 이거
Not this one.
연판이다.
연번하게는
뭐这个是什么标志？
这个要改名字。这里要改成 run thread， 你这个也是要改 run thread， 然后这个是不用这么拿的。你这个拿的。
Okay, you can see that the original, which is this original, is the same as the version 1, which is OIP critical version 1. You can see OIP critical version 2 also get the same result. That means these two produce the same result. Now you look at the performance. Is the performance bad? Very bad, right? Less than 1. 1 that means comparable. This is less than 1. It's 0.004. It's so bad. Why? Because I have to enter into critical region, come up on critical region 1 million times. And you see so slow there. But if you look at the second solution, YP critical version 2 is about 6.3 times faster. That means this is better. Right? Because I do all the hard work outside, and then I enter into critical region only 16 times. Okay, I don't have to do so many times, only 16 times. Okay, you see the difference there? Okay, the code not much different, huh? You look at the code. The version 1 looks like this. Like this. Okay, there's no partial sum here. And this sum is shared, because it's shared, and it's Greek modified right, but multiple threads, I have to protect it. Here, I also protect it, but all the for loop is done outside this critical region. And I can do that, it will not have risk condition because partial sum is local. Right? Only the sum that is shared and Greek modified right. So I only protect this when I do this task, but I do this task only one time. Okay? And because I got 16 threads, I'm going to do overall it will be 16 times. Okay, so it will be faster. As you can see the result, the result shows to you is faster, right? You can see that it's faster. Okay? So by looking at this solution, is this solution faster than this technique that we do without for sharing? Remember, we do padding, remember? We did this, the performance gain was only about 3. But now the performance is 6.3 times. So it means it's faster. Yeah? So if you look at the code, previously I did here.
在这边要修。
Okay, you see 3 here, 3 times. This one is for sharing. This one is for sharing. I solve the problem in multiple thread, but it's for sharing. This one I eliminate the for sharing. This one is for reduction. So that means our current solution that we did just now, using this technique, is as fast as the for reduction. For reduction, we got a quite good result, right? So that means this one is comparable to our for reduction. Yeah? So in fact, our for reduction also uses techniques similar like this. Okay? But of course, for reduction is the easiest of all. Because for reduction do all the hard work for us, including locking. If you look at the for reduction, you don't see any lock, only any of this lock here, because it's hidden behind the for reduction. Yeah? Okay, so I'll show to you 2 techniques here, version 1 and version 2. Okay? And and you can see also the result, which one is better. And don't do this. Although this one come up with the correct solution and you look at the solution, it's the same. This is the original. This is the one that I did, OMP principle, but this time. Okay, the solution is bad, performance is very, very bad. And the version 2, I use this time. And the performance is very good. It's as good as a fault reduction. Okay, our job is to come back here and try. Okay, this is the original code. I made some modification, and this is the one that you need to do for this one. You can try this. Call this version 1, call this version 2. Okay? So the version 1, if you try it, should be as bad as what I showed you. The performance is going to be not as good as well. This one should be better. Okay? But here I only put version 2 because I expect it to do this. This one you don't have to do it, but if you want to do it, refer to my version 1 to try and see whether you get the bad performance. Okay, change the code here. Do it now, I'll give you 10 minutes. And then we move on to question 2. Okay, question 2 will be similar exercise, but the code will be a different code. Okay, and then you try again. Let's try this one first. You try it now. Let me know if you have any problem.
所以在这个谷歌上面一起看。You try and let me know if you have problem. No?
就要开这个东西过来吗？
啊，开这个。
不开了，然后你是放到啥样？
等一下。你这不是开source file吗？你开 property。
哦，有啊，还是有。
你跟我的 code 一样啊。integer 没那些。
Okay, please find your group members and fill in the list. You should be filled in the group information inside the Excel sheet. I shared with all of you, right? Please find your group members and then put in the title. We'll submit by week 7.
那现在我们做吗？
啊？
现在我们做吗？
现在是他刚刚给的那几个非常多，你要跟着这个去，还有50号分布嘛，然后为什么刚刚我们这个原本的口做成我希望我生兔的功能出来，我是不会要照常发的这样。
我过来搞一下。 你这个照片发给我。
我宣布了，1楼也出在那个 folder，可以再过。
Let's go example. Show you. That is not for the. That is the final. Yeah. Yeah. That's what we put the literature itself. But it doesn't need to be completed. It doesn't need to be the final. You can change it as you go along, and then you submit again. That will be after you preferably in C++, but if I want to write in Python, but preferably in C++. But you can mix C++ and Python. So create a core. The reason is because we want to see its performance. Yeah, you can use Google Colab, but the program should be in C++. Because it runs in Python, because Python is C++. Here's an example. Regression is too simple. In that case, it's not really regression. Actually, that example is given to me. Actually, is given to me. That example is not really that one is distributed system. It's not ParallelComputing. So you need to know what it is. You want to choose ParallelComputing or distributed system. Distributed system is generally a number of computers. And then the distributed system. ParallelComputing you can run distributed system is make sure that you don't connect using either software or and also you need to, when you do the demonstration, you need to have multiple computers to show that it works. I think it is equally related because Suzuki becomes solid objectivity just like you can do and then show that it's actually a proper passing for it's actually solving the same problem. Okay, so Suzuki Kasami is just like that. insert it, distribute the lock. This lock is actually on the local machine. Security must have been already assembled in this yeah, it's actually actually do maybe one color JPEG, similar to JPEG outcome as JPEG, and then you compress the image. Okay. You compress using single color, and then you compress the color. It's not JPEG, but similar to JPEG. So we need to learn about this. Basically, the image is big budget, so 60 minutes and you it's a 3D PCB. Look at our different so frequency. So this one is on this is space. The space. Then when you convert to frequency, it's big like it as well. And then the top left there will be the lowest frequency, the high frequency. And what you can do is you try to quantize it. So it's try to
有可能这个，然后你要，因为还要不是那么顺利，那给我们3个version 1，只是用那一个水上，还有一个 version。
还有我们用 version 2做筛上。
就2个都要做出来，就 based on 这个的 based on 这个的，要改成 version 1。他找一大堆种种的这样，然后
too much quantization you get too smooth, low frequency, the image becomes big. Okay, but
完全跟不上逻辑。
but the low quantization, the image recovery will be good, but not much.
就听得懂特别是会死。
allow the user to choose how much to apply. After you quantize already, you say because the color, 3 colors are usable. 3 times this. But with 1 color, so what you can do is you can use frequency now to change the color picture into black or grayscale. And then you use So when you reverse it comes from frequency domain back to this but depending on how you apply the image can be okay.
我的口碑都大。
这是他颜分，来 test 他颜分，放着参考。
First one is using the
我申请的对象给这个 assignment 进来，进来。
Okay, this matrix is A by A is very small. So you do many okay, so each and then you also many. So every okay, so this is the good problem to solve. The one that I think you actually it was given to me by that one is just maybe the way it's right. Okay, how to put this in what-based conversation and what kind of matrix that is there is a recommended matrix and the recommended one is you get the matrix and then the
QB。
the matrix
因为我们做广播就是4、5个博士了。
他 report。
这为什么我们做的题目写一个 report， 关于谁跟他讲？
你有没有多equation？
这课完全不是equation，
这都是equation好然后
可以看我们做什么，我在写这个。
这equation是 online 考我是吗？还是？
就online找，是不是被找他的 Rachel？ 它是叫 theory 吧，然后我们的 topic 啊，我们找我们 topic 放是 equation。
然后这些 code 是
被找那些 equation 做出来，calculate gradient calculate 都是，刚刚那个
然后
它的方式，
选择范围是什么？
外面看。
还
比较累分这样子，因为你们，我觉得应该都会自己做吧。
这是proposal不是 report。
不懂，应该是这个 document entry 那个。
所以这个 assignment 日期就要交。
交report罢了，然后之后还有别的。到第12的时候要交 coding。
requirement report 它那个日期交 report 里面都需要把 code。
不过这是来 appear a problem in class, query estimate the problem, writing a project expression, let the teacher report, identify new resource object, and pick the algorithm. If you are using existing code, identify important and type certain functions.
哦，所以是 use existing code。
因为 propose 就是一样是 report， 只是一个草稿这样子先讲上去，然后我们做完了还要再多一个
Okay, for your
final
project,
report。
please don't
所以我
do
们需要自己
linear
做
regression, don't do Monte Carlo,
这需要
because all these are very, very simple ones. Okay? Do something more challenging. Okay, I suggest to you this book is image compression. Image compression like this. Okay? Then you can write quite a lot of things because you have to learn how to do DCT, that means the transformation from spatial space into frequency domain. And after that you do quantization and then you save it. Okay? Save it into the drive. And then you load it back, dequantize it, do the reverse transformation, back into the picture. Okay? So with one CPU and then one with GPU. Right? Okay, the first one you have to do it and then show it. You compress and you decompress it for the single CPU. And then with GPU as well. Compress it and decompress it with GPU. And then compare the performance gain. Okay? Solving using GPU. Okay, so this block here is small block in the picture. So you got many there, right? So you can use a GPU to solve this efficiently. Okay? So this one is picture. You can choose others. You can choose compression. This one is image compression. You can choose data compression. Image compression normally is loosey compression, meaning that the data can go missing without much deterioration to your picture. Okay, if data compression, it must be lossless compression, meaning that no data can be missing. Right? And we have many. You got like LZW, LZ77, LZ78, LZM or whatever that you find on the internet. So there is a lossless compression, data compression, and you can do also encryption, decryption, using triple dash, AES. Okay, these are suitable problem, real problem, suitable real problem to be solved using parallel computing. Okay, don't choose Monte Carlo. It's too simple. Monte Carlo actually has nothing much to do. And you cannot write much as well. Here you can write quite a lot of things because you need to know what is DCT, what are they doing, and how do you do the quantization. Okay, there are quantization matrix that is provided by JPEG. Okay, you can go to the standard and go and find. Okay. And also, of course, the quantization matrix depends also. Depends on how much compression that you want to achieve. Okay. So in your case, if you are doing this, you can allow the user to choose the compression level, whether you want it to be high compression rate or low compression. Right? High means if the image is going to lose a lot of information and then it's going to be blurred. Okay? And if the compression quality is good, meaning that you do not have much compression gain from that. Okay, so you can allow, like say for example, you want 10%, that means it's going to be blurred. 20% it is a little bit sharper. 90% then it will be very clear. Right? So you can choose from maybe 10 to 90%. Okay? So you can see the image from blur, which is poor quality, to sharp, which is good quality. Okay? And then you do the comparison with the CPU and GPU. Which one is faster and whether there is any performance gain. Okay, from all of the scenarios that you choose.
我这可以。 없어서
Okay, for this, of course, you'll be. It requires you to go and find out about the information. Yes, but you don't have to write the code yourself. You can go and find from the internet the code that has been written by somebody else. Okay, what you need to do is get that code to run on single CPU and then convert it to GPUs. Okay, refer to the code and then convert it to GPUs. That is what I need. I don't need you to create your own code from scratch. No. Then you can refer to code that's given in the internet. Okay, there's a lot of information that you can find on the internet that shows to you how to do it. Like for example, I mentioned to you that that's the quantization, right? And then when you compress it, you use this run line code. There are many ways. Run line code is the simplest one. So you go zigzag like this and use run line code to compress it. If you don't want to use run line code, you can use Huffman or arithmetic coding. So there are three methods there. Okay? Okay, this one is 3 color, but you don't have to do 1 color. Change the color to grayscale. Use OpenCL. Okay, OpenCL can help you change the color image to grayscale, and you can use it to display on the screen as well. Okay, so after you do before you compress, you display first, and then you compress and decompress and then display again. Okay. Right, you can do this using GPU. That means all this can be done by GPU. Okay, the compression, quantization, runtime, all in GPU. Runtime is the simplest of all compared to Huffman and arithmetic coding. It depends on which one that you want to use. But I suggest runtime coding because it's the simplest. If you don't know what they mean, go and find out. Then this will be your literature review.
Can we use an older CUDA library here? Because some of the family members have an older NVIDIA GPU, the new library will support.
Okay, if I suggest that you use Colab. Colab actually also use old GPU, Tesla 4. As long as you work on Colab is fine. Because if you submit, I will run it on Colab as well. Using Colab to run.
If Colab can I bring my computer and control you also?
During by right, if you run on your system, it should run on Colab as well. Okay? You should be able to run on Colab. What you can do is you can upload it to Colab and run before you submit. Or maybe you develop using Colab as well, if you want to.
The Colab stack is pretty low, will be pretty slow, right?
Huh?
The Colab, I don't think will be pretty fast. It's quite slow, right? It's like
No, it will run on the GPU. So it's not going to run slow, it's going to run fast. Okay? Maybe you're talking about the from your PC, you want to get the result is slow. Maybe it's going to be slow. Why I say it's fast is because this is a cloud service, right? So this is a PC. And this is a server with a GPU. The interface here is going to be slow because it depends on how fast they send the image across, right? But once you upload your data inside the GPU, inside this server, the data is already
要学什么
in the
algorithm？
So when it's solved,
你刚才那个
it's going
表
to be
是看
fast.
的，
It's as fast as your PC
那个
GPU.
闪没到讲，那个是 distributed system 不怎么的，
Okay?
他讲那是
Because you're
distributed system
actually
就不怎么适合。
using the computer and the GPU on the server in the cloud. Okay, if you upload all your information in there and then you run there, it should be as fast as your GPU on your local machine. Okay? Because the data is not sent while it is processing. The data is uploaded into the hard drive inside here beforehand. You got about 51 gigabyte of space here. Okay, you can upload it, 51 gigabyte, and then run the whole thing there. Okay? You are not transferring from your PC to the server on the cloud. No. You upload it beforehand.
我就想就是要我们自己做，是不是？
我刚刚发的照片是一个 suggestion，
你发照片吗？
在 Google。
我其实也没有 idea，我也不懂它的难度是怎样子。
四边难。
哦，
视频巅峰就讲过，这颗飞轮更高。
在老师那边讲 easy 吧 easy 吧。重点是他考试，他等下发音再出口的话，真的会死人。问 ChatGPT 加3.4个。
我在 ask， 我还问那
哦，你在问那些 GPT。
Okay, you have a question? You have a question?
请问这是在看电影吗？
个屁是吗？还是哪里？
每次这里都有声音。
跟我做别的课。
然后音乐课。
You need to have a problem. For example, you say faster, what are you trying to find? Answer faster, you want to find a trend. For example, say cancer is for example picture, and then the AI is able to identify this part of the picture. It's like a cancer area, and then it knows how to cluster. This part here is actually looks like cancer. I'm just giving an example. And that is image processing. That's why I asked you what machine learning, what are you trained? What do you train the machine? Yeah? Movie recommender actually not so. I think too simple. Because the data is too small.
是讲读书的读书的，他是以为我们是几例？
好像是太深高，分数很低。
Like data compression, it will be quite a large data depends on how many data. You can give 1 gigabyte of data, then then you have to learn something like you see terms like salting, then you have to use the which is longer than the last one. So there are certain terms that
走过多少人？ 我也是看。
that would be better because if you have actually the algorithm is very simple. And then you have data coming in using the same data. When you do integration, it's also based on the data. Just like this case, it's 8 by 8. The image here is very different, but you chop it down to 8 by 8. And then you solve the computation. In your case also the same, the data is going to be big, and then you drop it to block. Because the compression has a fixed size. Normally it's I think it's about 8 by 8. And then you do mutation, rotation and all that. And then you do to decrypt. And you can do this on each of these independently. Then you do better. First thing is you can show there's a real application. Right? And you can show the results when you compare. You click on it, and then you can show, okay, when you before the decrypt, it's okay, it's normal time. When you decrypt the time, you see it, and then you can decrypt it. You see different passes. Okay, you have to show all that before the performance. Yeah. Do the skill first. You can encrypt it. And you can decrease on the same because it's using single speed. And then using GPU, you have to do the same process to show it works. Yeah, only measure.
Must be a fully functioning system.
Then I can fit in any data, any large file. And then you can encrypt. That's what you encrypt. Make sure that you be able to decrypt with the same output. And not just one way, then you can decrypt. Alright, any other question? Okay, if you are doing a problem like this, mostly one don't follow the requirement because it's going to be tough. If you want to do GPU, you want to do OMP, everything else. Because this problem is tough. Okay? This problem is hard enough for you to each person focus on it. If you are doing this. Okay? If you are doing GPU, only GPU. Everybody is doing it. Oh, am I smiling? Yeah, it's so hard. It is fast. So I do this. It's fast. Very fast. This one he's going to do it. He might choose something else. He might choose maybe data compression. Say LZW. Many actually. LZ is actually based on LZ7. You can do LZ7 if you want something. There are many actually. You can try maybe. The variant also and Okay, this one I think we use it in zip 7 zip. 7 is actually based on this one. Usually 7 zip is yeah, so this algorithm, this one is not the algorithm is explained. It's quite short, but you have to know how to talk. This one is the order. This one is useless. Okay, and you can split that into blocks. So big part, maybe split it into chunks, and then you can press it using the so I did encryption. And it's also the same thing. You split them into multiple chunks. Keep the result exclusion. Depends on how you study the code. Okay, you have to learn the code first, and then by doing that, you can also get a lot of references inside the document. Because you have to learn how this thing works. A lot of put as a reference inside. So this is one example. The compression menu. You see all stuff with LZ. Because this three scientists who came up with it's based on dictionary. So all this algorithm is based on dictionary. Technique is the core technique is based on dictionary. There are many different types of compression. This is known as a dictionary based compression. That's why you see all the compression stuff. Okay? The name behind that is all the other computer scientific concepts. Yeah, you can use any common one.
Each point a separate encryption algorithm to.
Yeah, you can choose maybe to put there, the other one use glowfish is another one. Glowfish.
Goldfish is a good algorithm name. Second done.
Glowfish is actually this one went to a competition together with AES, but they lost. They lost. But then it's okay. They lost to AES. So AES was chosen. Because there was a time people come up with the competition. So all of them went to compete. But they lost.
These are made by individuals.
So AES actually is the original name is Ron John, because his name is Ron John, but they changed to AES. Because AES is the name that whoever wins is going to show up AES. So Ron John is the chosen one. So all this is, Glowfish is one of the is by this guy, Bruce Sherman. There are many. You can go in front of so the finalist is here these are all the ones you can choose. The is the one that won. The rest all lost. Here you can see two fish there.
Right.
But three fish.
Triple dash no. Triple dash.
Why every decryption method name as water animal fish and then they frog. What's that? I want to be an octopus.
Krypton.
Then you can look at all this and then choose any one of them.
Except my entity computation, everyone are finding Lego.
But I suggest that look at the top few because the bottom one is the loser. The bottom one you see it's negative, that means one positive, that means one good thing, but this is poor performance. See Ronald 77 one.
For why
Negative, that means this one negative, we find one particular flaw. This one you can find 60. Loki is the worst of all.
maybe we change the name to call 97.
Call 69 not bad.
And then use the GPU to improve the performance. The algorithm you can find the performance.
Okay.
But you need to understand, that means you need to have a lot of references inside there to explain what are they, and then how the compression encryption is done. With the slides. Most of them are quite simple. Okay. And computation. It is just like you shuffle cards there. So there are many different types.
So this one is quite old, 2000.
Yeah, this is quite some time already. But this one I think is quite good because up to now nobody is able to break it. Unless you have got quantum computer. Okay, you can go now. You can go now. There's no call. There's Loki. But don't choose Loki, choose the one at the top.
But I thought Loki also is considered AES.
No, they went for the competition, but they lost. The one, the winner will be named as AES. But the AES stand for Advanced Encryption Standard. So when it becomes standard, everyone will say AES. Sorry, run job. That's distributed computing. Yeah. This one is okay. But you have to do networking. Because that is distributed. Okay, you can go now. No. You have to use you have to do you cannot choose
喂，还录着嘞喂。
There's so many modules inside there. When you go inside there, you know many things to do. There's only one. No, the same. It's also quite hard. Yeah, so the same thing. There are many different parts that you can split. Yeah. When you do 100 coding, there's one already. Maybe you can split this one. And then you have to do DCT, high resolution, okay, the button name.